Hi, we're Group KKED. I'm Diego. I'm Kurt.
I'm Evelyn. I'm Gloria.
And today we're going to be doing the experiments on elastic versus inelastic collisions.
So you're gonna have to get close for these animations here. So for our first one, we're gonna have P underscore red. So it's gonna be the position of red using mass, velocity. We're gonna find the momentum, and the mass for red is 0.2, and we'll use that to find kinetic energy. So it'll be 0.5 times mass times velocity squared, since that's the equation for kinetic energy. The units is joules for that. For the mass, it's kilograms, and for the momentum, it's kgms. Now for the blue one, we're gonna do the same thing, same equation. It's blue equals mass times velocity. Mass is also 0.2, and we're gonna use the same kinetic energy equation because it's universal. So 0.5 times mass times velocity squared, and same units.
So for the first part of the experiment, we're going to find out not only momentum, but the kinetic energy of both the blue and red cars, the total itself, and it's going to be of the elastic collision. So we set up our cars. We're going to have up to the first clip on each side. So one clip, and we'll send our red car to the other side on the same thing for here. We have the magnets so that when they come towards one another, they're going to repel because we're doing the elastic portion. And so what happens is that to perform this experiment, we'll click both of the red buttons, and then we'll hit record, and then we'll see our results of the graph. 3, 2, 1.
So now we're gonna get our points with the multi-coordinates, so we can get our points before the collision and our points after the collision.
So now for the second part of this experiment, we're going to go ahead and going to find not only the momentum, but the kinetic energy of an inelastic collision. So we went ahead and turned our cards so that they don't repel each other anymore, but now they're going to stick using some Velcro. We're going to line up our cards in the exact same way. But in this case, they should now stick to one another instead of repel them. Okay, 3, 2, 1.
So we're gonna go ahead and select the multi-coordinates so we can get before and after of our collision. So we'll go ahead and click this, move it to before the collision, and then we'll select another one and move it after the collision. And then we'll move our values aside so that way we can actually read them. And now we have our values. Now that we're going to be adding a weight to the cart, we're going to go ahead and change it on our calculator. So we're going to change the red mass from 0.2 to 0.45. Since this measures 250 grams and the cart is 200 grams.
So now we're going back to that elastic where they repel, and now we're gonna add 250 grams to the red part, and now we're gonna start our experiment.
So when it comes to the actual calculations of this lab, we're asked to fill out the following chart, where we have the collection of our values for both the momentum P, right, and the kinetic energy KE before and after our collisions. We have both our elastic collisions and inelastic collisions, and then once, just like we said, right, before and after, and then both when we had the same weight versus when we added a little bit of that weight, right? And so I just want to talk about the math that you're not really seeing go down, but it's there, right? we know that momentum itself has to be equal to the object's mass times its velocity. So with that being said, anytime we see this P figure, right, and any of these, whether it be for the red or blue cars, and regardless if it's the same or different weight, this is that math that's going on, and this is what we had originally programmed back into our calculator at the very beginning of this experiment. And similarly, for kinetic energy, we know that it's always going to be 1/2 of our mass times our velocity squared. And so similarly, right, we have our kinetic energy, kinetic energy, kinetic energy, kinetic energy. And so regardless of same weight, whether red or blue, it's all going to, we're still going to use the exact same formula for either one. And with that being said, now we can actually total it up, and we go, let's say if we did some quick math here, right, negative 0.007, so then that's going to 0.008, so we know that's going to be 0.001, 0.003, 0.001, 0.02. Let's see, this should actually be negative 0.02, 0.01, negative 0.02. I'll figure that one out right now in a second. 0.02, 0.02, 0.04. I'll figure that one out. 0, 0.02, and finally 0 here. Give me a second. So I went ahead and placed those values into the calculator and got our last values that we needed for our chart. And so actually the next portion of the experiment is asking us to calculate the percent difference between our total momentum before and after the collision and the kinetic energy for the 4 cases that we're working with, right? And so what needs to be done is that we obviously need to compare, let's say, the total momentum of this, we compare this total momentum, and then we compare it to the total momentum afterwards. And then we'll do the exact same thing, but for kinetic energy, right? So kinetic energy beforehand, and then kinetic energy after. And we'll go ahead and perform those percent differences so that we can fill out this table. So just to recall, anytime we want to find any sort of percent difference, it's always going to be our new value minus our old value, and then divide that thing by our old value once more. Multiply this number by 100, and that will give you the percentage that you are looking for. If we applied this, we could do it for the entire chart. So let's do that. Okay, so let's just set up a few of the equations, and then I can punch it into the calculator. Let's say that we are setting up for the elastic collision and the momentum, given that it's the same weight, and we're trying to find the percent difference between the before and the after. We know that our before is 0.01, and we know that our after is also 0.01. So in this case, again, our new value is 0.1, there, and there. So this should give us that value. Let's set it up for now the percent difference of a different weight, right? Still the momentum. In this case, we're going to have our new value of 0.04 minus 0.02 divided by original value of 0.02. We'll plug and chuck that into the calculator. What else? We can also have now our kinetic energies, right? So our new value, 0.02 minus 0.03, 0.03. And then finally for the different weight, it would be, let's see, 1.47, 10, negative 5, and then subtract that out from the 0.2, divide that by the 0.02. That'll be its own equation. Okay, perfect. Almost done with these first 4 sets of values. Now we can move on to the inelastic collision side. And for the inelastic collision side, let's do the momentum of the same weight. And again, it's just going to be negative 0.02 minus 0.02. And again, these values are being all multiplied by 100. All right, cool. So that was the same weight. Now let's do the different weight, right? Where it's going to be 0.08 minus 0 divided by 0. And finally, we can move on to the kinetic energy. And that should give us to the fifth. Subtract out our 0.01, 0.01. Lastly, for the last set of calculation, should be this. I'm going to run back and go ahead and plug all of these into our calculator.
Okay, so how did you produce a relatively perfect elastic collision between the two cards?
So because of the two magnets that we have, they repel, so they push away each other, so we can get a better result.
So how did you produce a relatively perfect inelastic collision between the two cards?
The Velcro between the two cards makes it stick them.
So were there any other options to achieve our process, whether it be a perfect inelastic or elastic collision?
So inside of the lab, we can only use the magnets. So for the inelastic collision, instead of using the Velcro, we would have them be polar opposites, so they would stick to each other like this. Instead of repelling like this, they stick like this.
When we say something is conserved, the percent difference is near or far from zero, and why?
So when we say something is conserved, it means that its value, or at least the percent difference, is going to be a whole lot closer to zero. And that percent difference is closer to zero because the conservation of momentum, right? So when we actually find the percent difference of before and after the collisions, we want them to be equal to one another because that's explained by the laws of physics.
So although we answered these questions, I just want to wrap up as like our conclusion reflective paragraph statement and just say that, well, in this experiment, we obviously tested both elastic and inelastic collisions using our cards. And we found that the momentum stayed about the same before and after each collision, except with the fact of the difference of weights in the original, right? But regardless, this should, like in theory, right, matches the theory of momentum being always conserved. However, kinetic energy is the one that we see that is a little bit changed, obviously, right? When kinetic energy comes into play, we say that we're supposed to lose some of it. Anyways, when we made the collisions between the inelastic using the Velcro so that the cards would stick together, some energy was lost as, I don't know, maybe heat from the collision itself. To continue concluding, our results weren't perfect because, like, small errors, right? I mean, there's going to be friction, there's stuff that's not necessarily entirely into our control, as well as maybe time differences that we are when we're actually pushing the cards. But overall, I think the patterns of our results fit exactly what we expected. And now we just all understand how different types of collisions work, especially in real life.